So in this third part, I wanted to explore how Galilean transformations emerge from Lorentz transformations at small speeds, when speed is much less than speed of light. Now, I noticed that a lot of you call such things, when I have discussions like this, you call it proofs. It's not a proof. I'm not trying to convince you of anything, okay? I'm trying to give you a deeper understanding of something. So this lecture, I guess it's somewhat, I would like you to see it, although I'm not gonna quiz you on it, okay? And the reason I'm doing this is that you can see, you can understand things a little bit deeper, okay? So the question is, how do Galilean transformations emerge from Lorentz transformations when V over C is much, much less than 1? V over C can never be bigger than 1, but it can be less than 1, it can be much less than 1. And the idea here is this. So we have this gamma factor that reads 1 minus V over C quantity squared. I can write this a little bit more professionally. Now this thing, this whole darn thing is small. Let me give it a nickname. I'm going to call it epsilon. Usually we use letter epsilon for things that are small. So anyway, so I have gamma equals 1 minus epsilon to the power minus 1/2. You know what this looks like? This looks like this. So if this is epsilon, this is gamma. Well, when epsilon is 1, you have 1 over the square root of 1 minus 1. That's infinity. Epsilon is 0, this is 1. And in general, it will do something like that. So it blows up at epsilon equals 1. But here, you know, we're working right here, small epsilon, we're working right here. We can approximate this by the tangent line here. So let me zoom in. So this is, say, this is 0.1 or something like that. 0. I'm just going to blow it up. And so this is gamma. So the real thing looks like that, and the approximation looks like that. Okay. Now, how do we approximate functions? So if I have a function, f of x, okay, I want to approximate the function around this point. Approximate by a straight line. I want to do better, maybe I can approximate by parabola. Similarly, I can approximate this by a straight line. If I want to do better, I can approximate by parabola, and so on. This is called Taylor expansion. I know many of you are intimidated by that term, but all it is, it's an approximation. Okay? And so Taylor expand. Okay? I'm just going to give you what that Taylor expansion is 1 minus epsilon to the minus 1/2 is approximately, well, first of all, it's approximately 1. Okay, if you just have to guess, you just say 1. It's close to 1. When epsilon is very small, it's close to 1. Plus, there is a correction due to the fact that there's a non-zero slope. It's not exactly 1. So if you step a little bit at epsilon 0.001, it will be slightly different than 1. Okay? And if you want to be even more accurate, you would include quadratic terms, and so on. Okay, so now I'm just going to substitute. Okay, sub into Lorentz transformations. So what I get is I get x equals 1 plus 1/2 v squared over c squared plus all that dot 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 times the rest of the stuff. And t equals 1 plus 1/2 v over c squared plus dot 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 times the rest of the stuff. Now I'm going to distribute. So this times this gives me x prime plus vt prime, which you will recognize as the Galilean transformation, plus small stuff. It's small because this is small. This is small. I'm going to stop right here. I'm not going to write the small stuff. And what about the time? T equals t prime plus v over c squared x prime, which itself is actually small, plus even smaller stuff. The even smaller stuff happens when you multiply this by this, and then even smaller stuff happens when you multiply this by this, and so on. This you will recognize as a Galilean transformation for coordinates. Okay, and so what about times? So unless the event at coordinate xt or x prime t prime happens so far away that we cannot neglect this term right here, we again get t equals t prime. In other words, we recover the idea of absolute time, all clocks tick at the same rate, and so on. So intuitively, this says that while clocks don't actually run at the same rate, and this factor accounts for that slight asynchrony, these errors are small, so unless we go really far away, we can forget it, and then it looks like clocks run at the same rate. So let me draw what I just said. Remember, in the previous lecture, or oops, I don't know why this happens. I drew these things. All clocks in frame S is synchronous, in synchrony, they all read 0. And then the ones in frame S prime, they're not. And remember, these are slightly lagging behind. This is lagging behind even more. This is slightly advanced. This is advanced even more. But when V goes to 0, that asynchrony becomes less and less perceptible. So unless you go really far that way, for that effect to become noticeable, you can forget the fact that these are not synchronized. And that's what basically this is saying. You see, so unless you go really far, unless X is so huge that it offsets the smallness of this. V over c squared is really small, and it's a measure of asynchrony. So unless you go really far that this asynchrony becomes pronounced, then this term is small. You go really far away. So there's always asynchrony, but the smaller the speed, the less pronounced that asynchrony is, so that this term only becomes important when you compensate for that tiny asynchrony by going really far away for this asynchrony to pile up. That's what this is saying. In any case, we get our Galilean transformations back. And that's what's going on at small velocities. It's like an emergence of approximate transformation in the limit of v going to 0 or v over c much, much less than 1. Okay, so this is, again, I'm not going to quiz you on that, but I want you to understand. I would have loved it if you could appreciate this and understand how we get back non-relativistic effects from relativistic effects. And this happens in physics all the time. Whereas there's one theory, and someone finds something wrong with that theory, they have to go back to the drawing board and redo the whole jigsaw puzzle just to get the new stuff correct. And it gives a totally different explanation to everything. And the old explanation just becomes a limit of this more correct new explanation. So a lot of people sometimes say, oh, scientists, they always change their minds. They don't. They just find better and better explanations of reality, such that the older explanation, it's still true, but it's now seen as a special case of the newer explanation. Okay? All right. Well, I hope this is resonating with you. Thanks.